All right. So now I will talk about a last bit of mathematical statistics that we will need uh, in future. So this has to do with basically the change of variables. Okay. So let me call it change of variables and and its impact on, let's say, mean and variance. Okay, so I will state the problem so that you have a better understanding of what I am trying to say here. So by this problem I mean that suppose you have set n number of random variable. So suppose n random variables that I denote by a vector x, and that has x1. So the entries are x1, x2 up until xn. Okay. So all these x1 is a random variable, x2 is a random variable, and they are distributed according to some joint PDF. So these random variables are distributed. So these are distributed um, according to some joint PDF that I call fx. So this fx essentially means fx1, x2, dot 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 up to xn. That means it gives you the probability distribution of simultaneously finding x1 at between x1 plus dx1, x2 between x2 and x2 plus dx2, and so on. Okay, simultaneous. So this is my joint PDF and the combined PDF for all the variables. Okay, and suppose this is not known. Okay, so suppose this is unknown. Okay, we do not know this joint PDF. What we know is uh, the mean and the variance of these x's somehow by experiment or something. Okay, so but the mean and the covariance matrix are known. Okay, so the mean is given by, so the mu vector is given by the mean of all those things. So mu1, mu2 up to mu n, and the covariance matrix is of course uh, Vij. This is the covariance between xi and xj. So this is the covariance between xi and xj, and this the mean means the kth mean. So mu k is equivalent to expectation value of xk. Okay, so these things are known. Okay, now I define a quantity. So now we define, say, y, which is a function of my uh, random variables, y equals yx, with a functional dependence that I that is not specified yet. But suppose I define a quantity y is equals to y and yx. I want to ask what is the mean and variance of this new variable y in terms of the old ones. Okay, so the question is uh, what are the mean and variance of y in terms of this mu vector and Vij. Okay, this is my statement of the problem. So, as you can easily understand that this covariance matrix, okay, that is the that kind of gives you the standard deviation of the mm, of the random variables in the xi xj basis, the x basis. So they will impact in this here. So basically, suppose I have a definition, so y equals x square. Okay. So the so how accurately you can measure y will depend on how accurately you can measure x. So that is my essential point here. So this Vij will impact the standard deviation of y as well. The question is how exactly will it affect? Okay. Now the answer can be found in the following. Okay. So first of all, we have to expand y um, in the neighborhood of the mean. Okay. So let us Taylor expand uh, yx in the neighborhood of mu. So what I will write is this. So y at x would be approximately equals to y mu plus say I equals 1 to n if I have n random variable, then del y del xi or del xi at evaluated at x equals mu times xi minus mu y. So this is Taylor expansion up to only the first order term. Why does this Taylor expansion make sense? Because even if I do not know the original distribution fx, if we can assume that this fx is sufficiently peaked around the mean, that means if I randomly sample x, it will be sampled mostly in the neighborhood of the mean value of x. Okay. If the fx is sufficiently sharply peaked. Okay. Of course, this expansion will not work in general, but for most of the practical scenarios when this fx is well peaked around the mean, that means the random sampling of x comes from the neighborhood of mu mostly. Okay, that means this yx, this arguments x, they are never very different from mu y or from this mu. Okay, so that's why this makes sense. Okay, and in the limit that this expansion holds, I can find out the expectation value of yx is simply y mu, basically this the first term, because the second term, the expectation value of xi minus mu y is 0, because expectation value of xi is itself mu y, because according to my definition this is equals to 0. Okay, so that means the expectation value of yx is y times mu. So what is the mean value of yx? Basically you replace this x by their corresponding means and you get the mean value of y. Okay, so for example, when you suppose in your undergraduate physics experiment, you had this, suppose you calculated the Young's modulus in terms of some displacement and some sort delta x over say L, something like this. Okay, and you measured this delta x several times, you measured this L also this several times, and you averaged it out. Okay, now what is the average value of this y? So at the place of this delta x, you plugged in the average value, and in here in for this L also you plugged in the average value, and you said that this is the average value of my y. Okay, so this is what you did in your. So why does this occur? Why does this make sense? It makes sense because of this. So you construct uh, uh, yx, here the Young's modulus y, as a function of the random variable. What are the random variable here? This delta x and L. Okay, so why are those random variables? If you measure, suppose you are measuring the length of the rod, okay, at some point, no two measurements will give you exactly identical results. Okay, no two measurements will give you the exact same values. Okay, what do you have to do? You have to basically take an average of that, but you can be sure that although those, that's why those are random numbers, but those random values are kind of peaked around the average length of that rod. Okay, so that if that rod is a 1 meter, you know that your measurements will be peaked around, let's say 1.01 meter to let's say 0.98 meter, something like that. You will every time you measure, you will get values in the neighborhood of that mean length, and that's why this xi, for example, if x1 represents the length of the rod and this x2 represents the displacement, uh, then those are kind of random variables, but they are basically fluctuating around some mean value. Okay, and you know this mean, if you know this mean and you know that if these are sufficiently peaked around those mean values, then your yx is just y at the mean values. Okay, but if it not the case, then you have to expand it to higher order terms, and you have to take into account the effect of the higher order effects. Okay, the effect of the higher order terms. All right. Now I need to calculate the sigma y square, the variance. Now if I want to calculate the variance in terms of y, so I call this sigma y square. So sigma y square will be given by expectation value of y square, I mean y square x, minus expectation value of y whole square. All right. So this is expectation value of y square x minus this is expectation value of yx is basically y mu. Okay, this is y mu whole square. Okay, so this is the thing. So basically I have to calculate expectation value of y square x. All right. Since I already know that yx is this, the expansion of yx is given by this thing here. So y square x, if I try to construct my y square x, it can be constructed very simply. So y square x is basically uh, yx times yx. Okay. Now yx you have to substitute here. So this is y mu plus summation over I equals 1 to n del y del xi evaluated at x equals mu into xi minus mu y. So this is my first yx. Okay, let me put it like this, and let me put this bracket in this color, and then there is the second yx here. So this will be the same thing with a different index. So this is y mu plus summation over, here I will use a different index so that I do not confuse with the dummy index I in the first term. This j equals 1 to n. This is del y del xj, x equals mu xj minus mu j, and then I close my bracket. Okay. So if I multiply these two, the first term is simply y mu whole square. Okay. And the second term is, notice carefully. So second term is, first this term might get multiplied with this term and it will give you y mu times the sum, or you can have this term multiplied with this term. You have y mu multiplied with the same sum. Okay. So what you have is 2 times y mu. Okay. And summation over I equals 1 to n del y del xi evaluated at x equals mu times xi minus mu y. And then in the second term, basically this is this term multiplied by this term. There is a double summation. So I use a different color. So I have a double summation here with for I and j, and I have del y del xi times del y del xj evaluated at x equals mu times xi minus mu y to xj minus mu j. All right. So now if I calculate my expectation values, so I take the expectation values at the same in the same time. So remember, on the left hand side I have this, the right hand side this, this, and this. Okay. Remember, so expectation values of this is equals to this, because this times expectation value of 1 is just 1. Expectation value of this is 0 because the expectation value of this term is 0. And then I have to take the expectation value of here. Okay. So basically if I calculate sigma y square, which is expectation value of y square x minus y mu square. So this, the first non-zero term, the leading order term is just this. Okay. So this is summation over I and j, okay, del y del xi del y del xj evaluated at x equals mu, and then expectation value of xi minus mu y minus xj minus mu j. According to my definition, this is precisely the covariance matrix, right? So this is my Vij. All right. So that means I get this relation, this very interesting relation. This is sigma y square equals summation over I j, then del y del xi del y del xj. Yeah. Then there is Vij. This is the standard deviation, formula for standard deviation. Now, if your starting variables are uncorrelated, okay, so if Vij is diagonal in x basis, so that means x1, and there are no correlations between x1, x2, x3, x4. The different x's are not correlated. If that is the case, then this Vij is diagonal and VII are just sigma y square. So for this equivalent is equivalent to summation over I, okay, del y. So this Vij would be del. So this is basically sigma I square delta ij for uncorrelated xi's. Okay. If the xi variables are uncorrelated, then this Vij is just sigma I square delta ij. So this is then delta I delta xy square. So the j summation drops out because it did this sum times sigma y square. And this is the famous formula for error propagation. So this is the formula for error propagation. Okay. If you have correlated event, then you should use this formula. If you have uncorrelated variables, then you should use this one over here. And you have been using this formula, I guess, for a long time. So suppose you have only two variables. Suppose you had, so let me do now examples. Okay. Suppose we have only x1 and x2. So there are only two variables, x1 and x2. Okay. So and you construct first y equals x1 plus x2. Okay. So then quite clearly the average of y will be just mu1 plus mu2, and the standard deviation, so sigma y square, will be given by del y del x1, which is 1, del y del y1, which is 1, and according to this formula here, okay, I will have sigma 1 square plus sigma 2 square plus, if there is a correlation, then there will be 2v12, but if the correlation is 0, in the limit that this correlation is 0, this is simply equals to sigma 1 square plus sigma 2 square. So unlike the mean, here you see the errors are added in quadrature. That's why you sometimes hear for additive and subtractive events. So it is true, also true, instead of x1 minus x2, instead of x1 plus x2, you have x1 minus x2. Okay, this is also true there. So the errors are added in quadrature. Unlike the means, the errors are added in quadrature. So uh, if you make delta x1, or if you make sigma 1 error in measuring x1 and sigma 2 error in measuring x2, then the error that you have in y is sigma y square equals sigma 1 square plus sigma 2 square. All right. Instead, if you have a product or a division of two variables, let's say you have instead y equals x1 times x2. So that means delta y delta x1 um, equals x2, and delta y delta x2 um, equals x1. Okay. Then if you try to figure out the sigma y square, okay, so if you calculate sigma y square here, okay, so this delta y delta x1 equals x2, you can write it as, this can be written as y by x1, and this can be written as y by x2. Okay, so if you apply this relation, these relations in here in this formula, yeah, for uncorrelated variables, or rather let's say correlated variable, then you will have this relation, this sigma y square equals delta y delta x1 means y over x1 square, this y square by x1 square times sigma 1 square plus y square by x2 square times sigma 2 square plus 2v12 then y by x1 into y by x2. Okay, so you can take y square common from the numerator of this side, and you can cast this as like this. So sigma y square by y square equals sigma 1 square by x1 square, sigma 2 square by x2 square, plus 2v12 by x1 x2, that is again y. All right, so what we learn is that if my variables are related by a product of two random variables, then we add the relative error. So then the relative errors are added in quadrature. Okay? So in the limit that this go to 0, then I will have sigma y square by y square equals sigma 1 square by x1 square plus sigma 2 square by x2 square, right? So these are the simple things that you have used in your calculation perhaps somewhere. Uh, so in general, the formula is given by, the error propagation formula is given by this. But if you have special cases, then you can simplify these things like this. Okay. And if y is more complicated than just simple product and sum, then you have to use the actual formula. All right. So I will pause for a brief moment here, and we'll try and see if there are any questions here. So this should be quite easy, and can carry on. Any questions? All right. Okay. So hopefully this was clear then. Now, a straightforward generalization that we can do is that instead of one y, if I had created a number of y's, okay, so you see here, I had only y variable, only one variable that I made up of these x variables, and I created this one. But instead of that, what I could have done is that in general, what we do, we create a number of variables. So suppose I create y1 equals y1x, and so on up to, let's say, ym equals ymx. So combining these x's, I now create multiple y variables. Now I want to know how the correlation matrix, or basically the covariance matrix in the y basis, will be related to the covariance matrix in the x basis. Okay, so what I can define a covariance matrix in the y basis. Okay, so suppose I have y alpha equals y alpha x. Okay, here alpha is 1 up to m. Okay, and I have n variables, and I have created m number of alphas. Now I can create a covariance matrix in the y basis. Okay, we will denote it by u, and I call this u alpha beta. So I use a different index. I use the Greek indices to denote by my y basis, and my Roman indices to denote my x basis. So this is essentially defined as covariance of between y alpha, y beta. Okay, and as a straightforward generalization of this rule here, so remember, this should be the diagonal elements of u alpha beta, right? So these should be the diagonal element of the u alpha beta, because the diagonal elements in the u basis, in the y basis, are precisely the covariances of my y variables. Okay, so the diagonal elements would be this. So the off diagonal element would be just y alpha times y beta. Let me write it down and you can easily guess. So this is a straightforward generalization. So this will be ij equals 1 to n. You can write it as del y alpha del xi times del y beta del xj. Okay, this times Vij. Again, by definition, it's a symmetric matrix if Vij is also a symmetric matrix, which it is because Vij is a covariance matrix. Okay, so remember this Vij is the covariance between xi and xj. So by definition, it's a symmetric matrix. So the covariance in the y basis is related to the covariance in the x basis via this rule. Okay, remember for alpha equals beta, that is here you put alpha equals to beta, that is the diagonal element of u, you get back the relation of sigma y square here. This is del y del xi del y del xj times Vij. So you get back this relation in the diagonal limit, and this formula makes sense. Okay. Now you can cast this relation in a fancier notation, so that uh, the our knowledge of linear algebra hmm, can be uh, can be applied here. Okay, so I always forget to mention that it is evaluated at x equals mu. So you should always remember that this little thing is always there, which I forgot to use here. But here it also means that these are evaluated at x1, the mean values of x1 and x2. So these are evaluated at x equals mu. All right. So first of all, I will define a matrix A whose let's say alpha ith element will be given by del y alpha del xi evaluated at x equals mu. So this is my definition of this A matrix. So A matrix has two indices, alpha and I. So this will be a m cross n matrix, right? Because alpha runs from 1 to m, I runs from 1 to n. So this runs from 1 to m, and this runs from 1 to n. So this A is a m cross n matrix, right? Okay, all right. So then, in using this definition, you can write the above relation as this u alpha beta is equals summation over ij. Obviously, the sum runs from 1 to n. Del y alpha del xi is basically a alpha I times del y beta del xj is a beta j, and this is Vij. Okay. Now you rearrange this term. So this is summation over I and j, and then you have a beta j. No, sorry, a alpha I, Vij, then a transpose j beta, because a beta j is the j beta element of a transpose, and this essentially gives you, using the rule of the matrix product, this is a times v times a transpose. Okay, and this matrix multiplication of course makes sense, because as I told you, a is a m cross n matrix, v is a n cross n matrix, and this a transpose is a n cross m matrix. So the whole matrix is a m cross m matrix, and this u is again a m cross m matrix. So this is in terms of linear algebra, if you define this matrix A, which is defined as del y alpha del xi, in many ways, this is the Jacobian, okay, and here uh, you have this, okay. So then you have the correlation matrix basically transform as an orthogonal transformation of the correlation matrix in the old basis. So the correlation matrix in the old basis and in the new basis are just related by a orthogonal transformation. That's it. This is essentially the rule. Okay. One interesting application of this is that if you do a linear transformation of matrices, okay, so notice, suppose the implication of these A's are uh, in the uh, in the case of the linear transformation, so what I have here, suppose I have,
Sir,
yes,
sir, the transformation is orthogonal transformation, but it does not
no,
mean
no,
that.
no. It's not a. I should not say it's an orthogonal transformation. Sorry, this A is not necessarily an orthogonal matrix. Okay, it's a matrix, but since the transformation looks like a transpose, I meant it to be orthogonal transformation. I should perhaps say it's. So this is the structure of the transformation. I should not give it a name. Okay, all right. Uh, it will be orthogonal if I define it to be. Okay, so this A is not an orthogonal matrix. Yeah. You are right if you are pointing towards that.
Okay.
All right. So this now, as a special case of this, I can construct a linear transformation. Okay, and this linear transformation, in general, it can be an orthogonal transformation. And why it will be an orthogonal transformation, we will see. Suppose the special case is this. So y alpha equals j equals 1 to n a alpha j x j. Okay, so this is a, so basically um, I create my y alpha as a linear transformation in terms of this xj. Hmm. So here again, now I have alpha equals 1 up to n and j as well. So the dimensionality in the y space are the same as the dimensionality in the x space. Okay, so in explicit form, because people who are not familiar with linear algebra, so the explicit form, if you construct y1, this will be a11 x1 plus a12 x2 plus dot 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 up to a1n xn. y2 equals a21 x1 plus a22 x2 plus dot 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 plus up to a2n xn, and you go carry on like this, and this yn will be the an1 x1 plus an2 x2 plus dot 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 plus ann xn. Okay, so suppose this is the transformation I defined. So that, so in the left hand side I also have n number of y's, and I am basically shifting from n number of x's to n number of y's. And why do I shift that? Hmm? So notice the difference between this and that. So at the beginning, when I started with the transformation, I did not mention about the nature of the functional structure. So yx can be any arbitrary function of x1, x2, and xn. Here, in this particular case, y, the functional form of this y in terms of this x are all given. and the functional dependence is just linear functional dependence, okay, with these coefficient a11 and a22 and so on. Now if you actually extract this derivative, this del y alpha del xi evaluated at whatever point, this will actually extract out the coefficients. So this is how you extract out the linear coefficient. So in this, this definition is by design consistent with this definition of the Jacobian matrix like this, okay. And so I can basically automatically say that this a alpha j by construction is del y alpha del xj evaluated anywhere, okay, because you see this, and suppose you take del y1 del x3, and that will take you to a13, okay. If you take the derivative, you match for any alpha and j here, uh, it will match, okay. But the important point is here, from the very beginning I have started with a linear dependence of variables, okay. But remember, my previous analysis was completely general. So this rule will be this rule will be holding true no matter what the transformation rule between x to y is, okay. So remember, if you are trying to visualize, so you have a x space, data in x space, okay. So this is my x space, and you are trying to map it to y space, okay. So this is my y space, okay. And this mapping rule can be anything. I am always transforming from a x space to a y space. I am trying to redefine my variables, and why I need to do that, you will see slowly examples of why we are doing such things, okay. And in the special case that this transformation rule is linear, so this is, I call it linear transformation, so that this holds, that means the coefficient matrix, that is this del y del alpha del xj a alpha j, it's a constant matrix, okay. It's a constant matrix no matter at which x you are looking at, okay. It's a constant matrix. But then, so the then what is my essential point? My essential point is to relate the covariance matrix in y space to the covariance matrix in x space, okay. So the covariance matrix in y space, so this is U, this should be equals to, it should be related to my covariance matrix in x space, and it will be transformed like this. So A, V, A transpose, where this A matrix is precisely this A11, A12, and so on, so on. This is the A matrix, okay. Now you come to this conclusion. Now, the important thing is that suppose you start with a x space, you start with a number of variable, these are denoted by x1, x2, and blah blah. There, it was a non-diagonal matrix. Suppose this was non-diagonal. That means there exists a non-trivial correlation in x space. So there, the correlation matrix is non-diagonal. My point is to show you that you can transform to a y space via a linear transformation, so that the new correlation matrix or the covariance matrix, I am using it interchangeably, but you should understand this is a covariance matrix, so this will be diagonal. So this is the whole point of transforming. So if my covariance matrix is diagonal, there are certain leverages that I can use in my calculational thing, okay. I do not have to worry about correlation between different variables. If I can transfer myself to a space where the variables are not correlated, okay. And the theorem of linear algebra tells me that such a transformation is always possible. Why? Because even if this is a non-diagonal matrix, this V is a real symmetric matrix. By definition, V is a real symmetric matrix. So this is a real symmetric matrix. Okay. Now, if this is a real symmetric matrix, then it can always be diagonalized. It can always be brought into a diagonal form. This is a standard eigenvalue problem. Okay, it can always be brought into the diagonal form by choosing A suitably, by suitable choice of orthogonal A. Okay, so here comes the use of your lessons from linear algebra. So if you are in a basis where the array of random variables that you have in your hand has a non-trivial correlation among them, or the covariance matrix is non-diagonal, then it is always possible via a linear transformation to transfer yourselves into a new basis. You can call it the basis y, where your random variables are given by y1, y2, and yn. Those are related to your x1, x2, xn by linear transformation, such that in this new basis, this y1, y2 basis, the variables, this y1, y2, yn variables, are not correlated at all. The covariance matrix is diagonal, and more often than not, it is much more convenient to work with uncorrelated variables than with correlated variables. Okay, so you can use this lesson to, if you encounter such a situation, remember you can always transfer yourself into an alternative basis. Okay, so this is the essential point of this part. Now again, this is very crucial because here I will stop my mathematical statistics, like the formal theoretical statistics part here. So let me know if you have any questions up until this point. Any questions? Okay. So since I do not hear anything, I just assume that things are all right. Mm, just let me have some water, then we can continue. Okay. So let us resume then.
Hello. So,
Yes.
sir, as you have shown here the linear transformation for y,
Yeah.
uh, we can also have a different transformation as given in the above matrices. Means we don't need necessarily a linear transformation for
Uh,
this property.
unless you have a linear transformation, this A will not be a constant matrix.
Okay, okay, okay.
Right? Okay. So now I will move to the application-based statistics, and here uh, we will discuss something called statistical test. Or I would like to call it inferential statistics, or the statistics of inference. So statistics and inference. So that means basically decision making. Okay. So here we shall discuss how we can perform statistical tests designed in a suitable manner to make decisions. Hmm? Now, what kind of decisions are we talking about? We have to make this thing more precise. That what I mean by decision and what kind of conclusions we expect to draw from statistical tests. Okay. Now, I will broadly classify these things into three categories. Okay, so we will be performing three categories of statistical tests. So that is so I will have let's say three categories. Now, listen very carefully here, okay, and try to think over it. So first category is you will have two hypotheses. You can have more than two, but you have you mostly have the like two hypotheses, and you have to choose one or the other depending on the data. Okay. So what I mean here, suppose you are running a fishery. Okay, suppose you are running a fishery. I do not need to write this, of course, huh? And suppose there are only two kinds of fish that you grow there. Okay, so just for fun, let me call it hilsa, and another kind is, let's say, rohu. All right. Now, I'm not sure if these two things grow together. Of course, one is salt water, another is sweet water. But let's not take those kind of finer details into account here. Uh, uh, but suppose you are growing it in the same pond, and at the time of your harvest, when you are catching the fish, then you are catching in bulk, okay, and all the fish are being caught as a result. But these two fish are sold in the market in two very different prices. Okay, and I mean one is more expensive than the other. So you need to sort it out properly before sending it to the market, because one bunch will cost substantially higher than the other. Okay. Then, so what will you do then? Okay. You will then hire a person. Okay. That person, of course, is expert in fish, in identification of fish, and that person manually goes through the bunch of the catch that you have here and manually sorts this out. Okay, so uh, checking these properties. Okay, this one the gill is a bit more reddish, so this is hilsa and this is rohu and so on and so on. And this guy does manual labor and he gets paid for that. Okay, now you want to automatize that thing. All right, so when I talk about two competing hypotheses, I mean situations like this. Suppose hypothesis one is hilsa, so this is sometimes is I denote it by H0, and rohu is my H1, so this is my hypothesis H1. All right. Now, since you are clever and you are a business person, so you want to make profit, so you want to cut down the middleman who is manually going through this procedure and selecting hilsa and rohu based on his eyesight. So you realize you can automatize that process. So this is a cliched process that goes on and on forever. Okay, the same thing is being repeated by this person. So you want to identify what are the properties that this guy, when he is sorting this hills and rohu manually, what properties are he looking for, and you want to learn that. You want to train a computer to do the same thing, and the computer will look for the same properties that this guy is looking manually. This these properties, and based on that decision, based on that property, uh, it will either conclude it's a Hilsa or a row. All right. So suppose this guy is looking at certain properties, right? The average diameter of the scales, or the width of the fish, okay, or the from the length, let's say from eye to the tail end. Okay, so these are the combinations. So these are data that this guy is looking at. Okay, so I call this data to be X. Okay, the X vector. So X vector is an array of data that contains information about the product and about the thing that you were testing. Okay, so it can be the length of average length of the scale, average, let's say, width of this, not average because you have only a single thing. Yeah. And based on that, he is making a decision. Okay. Now, suppose you have a computer and you learn how this guy is doing it, and you train that computer. So if you see this much length, that much width, and then make this decision, so that the computer is trained to do that. Now here comes actual scenario. Here comes actual scenario. You are given a fish, and the computer sees that the fish has length equals this much centimeter. Okay, the length of the scales average of the is, let's say, 1 centimeter or 1.01 centimeter. Uh, and based on that, it has to make a decision whether it is a Hilsa or a Rohu. Okay. So this is the first case scenario. So and you want to sort it out. You want to sorting of data. Okay. So if this is the scenario, I will class this category. The first category is uh, sampling of data or classification of data. Okay. Now the second category, okay, uh, second category is a special case of the first category. So in the first category, what you have, that you have two competing hypotheses. So one is like is H1 and H0. Notice what you are doing here. So based on data, when you have a particular array of data, you have this observation. So this is your observation. Okay. So based on this observation, all right, you will either accept this compared to this one, or accept this compared to this one. So when you are basically making a decision, you are basically comparing hypotheses. So basically comparing your which hypothesis is more likely to cause this data between this H0 and H1. Okay. So suppose you have this data and you have these two hypotheses. You are trying to compare the probability that f of x given hi. Okay, so I equals 0 or I equals to 1. So what is more likely? Okay, so if H0, so if you at one point you place I equals 0 and calculate this probability, and you place I equals 1 and calculate this probability, you calculate which one is higher, and based on that you make a decision. It might be as simple as that. Okay, so but if you do not have competing hypothesis, suppose you only have H0, because it might be it might occur that you do not have a competing hypothesis and you have only one hypothesis, and you need to make a quantitative remark about how good is your data, how well is your data uh, being described by the hypothesis. Okay. So, for example, So you want to make um, a quantitative statement um, about the extent of agreement between the theory and data. Okay, but theory, I mean, it's a well-defined theory. I will define properly what do I mean by well-defined. But the important thing is that you want to make a quantitative statement. You will not make a vague statement. Yeah, it more or less is it agrees with the data. You do not want to make such a statement. You will make a quantitative statement. You will say there is a 30% agreement, there is a 50% agreement between theory and data, something like that, and it must mean something. So it's a quantitative statement about the extent of agreement between theory and data. The example of this kind will be, suppose uh, suppose in IIT Indore, okay, we have now a total of 2000 students, okay, and you calculate the gender ratio, and you find that there are 1110 males, and the rest, which is around 890, I guess, are females. Okay? Suppose these are the uh, apart from saying females and females, maybe boys and girls are better. Okay, so there are 11 and 10 boys, and there are 890 girls. Okay, so this is your data, and you want to make a quantitative statement. This is how compatible uh, is this data uh, with uh, the equal ratio or the gender unbiased hypothesis.
Sir,
Yeah.
in number two, you have written the theory and data agreement. The theory means hypothesis here,
Yes,
right?
theory means hypothesis. Yes. Yes, between the hypothesis. If you okay. Now remember, suppose we would ideally like to think that our country is gender neutral, right? That there is no, let's say, explicit discrimination between men and women. Okay, at least at a theoretical level. Now, even if that is true, in an actual sample set, if you actually go to educational institutions or let's say other institutions where your where this kind of gender studies matter, and you actually count the number of boys and girls just by looking at in one institution, and you see there are you will never, suppose if you have 2000 students, it will never occur unless you are extremely lucky that there will be exactly 1000 boys and there will be exactly 1000 girls. Okay, there will never be true. There is always fluctuations. Okay, for example, if you see the gender ratio in physics, let's say you will have more boys than girls, but if you go to opposite doctrine, let's say biophysics or psychology, you will see more girls than boys. Okay, overall maybe uh, but let us talk about total students, and you see this 11 10 and 890 girls, and can you, now, your hypothesis is that our institution is gender neutral, and there is no visible bias in that. Does this number, how compatible are these number with that hypothesis? You want to make a quantitative statement about that. So you have this observation. This observation looks biased, let's say, at a plain sight. Okay, And if someone sees that, oh, and there are 200 more boys than girls, and they can interpret. I mean, remember, there are a lot of ways to misinterpret statistics. So do not fall into those traps. Okay, you need to learn. You need to understand uh, what kind of statistical conclusions are you going to make, and based on what kind of data. Okay, so if you have this observation, and if you just say, because even if there is a unbiased hypothesis, it can lead to that data this extreme, of course. But what is the probability of that? We have to figure it out. Okay, and then we have to talk in terms of that probability. Okay, so this is my uh, category 2. Okay, so I talked about three categories. First category is the sampling of data, when you have two competing hypotheses and you are trying to choose one in favor of the other. You are trying to sample data. Then you are in the next example, you do not have a competing hypothesis. You have a single hypothesis. Okay, and the hypothesis needs to be simple hypothesis. I will define in the next class what I mean by simple hypothesis. And in this example, what you are trying to do, you have only one hypothesis, and you are trying to make a quantitative statement about the extent of agreement between these two. And this type of analysis I will call as the goodness of fit test. Okay, so goodness of fit test. All right, and then there is number 3, which in particle physics will be our kind of most common. Uh, Actually, in particle physics, we will encounter all these three kinds, but most common is this number 3, which is to say, your hypothesis has a parameter. Okay, so suppose your hypothesis uh, depend. I will use hypothesis and theory interchangeably. Depends on parameters, certain parameters. Okay? Usually the parameters would be expected as lambda, or rather, I will denote it by theta. Theta is the more common. So theta 2, and suppose there are m number of parameters. An example will be, suppose um, suppose you are trying to measure uh, the the Planck's constant, let's say, using atomic spectra. All right, you know the Rydberg formula, that if you see an atomic spectra, the different energy levels, basically, they are separated by energies that are given by like 1 over n1 square minus n2 square, and you see the color of this thing, and you try to figure out what is the value of the Rydberg constant. And let's say, yeah, you are trying to figure out the value of the Rydberg constant. Let's say, what is the value of the Rydberg constant? Okay. So, so what you calculate is delta E, right? How do you calculate the delta E? So you calculate delta E by measuring wavelengths. Okay, and you do not exactly determine this wavelength. What you calculate is basically, let's say, lambda plus delta lambda plus minus delta lambda. Let's say you have a ratio, but for now, let's say you know the lambdas exactly. You have an array of wavelengths. Okay, now you have data. So these wavelengths are your data. So let me call the wavelength as x. So x1, x2, x3, these things that you have measured. Hmm? And my delta E kind of is predicted from a hypothesis, but in terms of an unknown parameter R, that is my Rydberg constant. Okay, so the Rydberg constant gives you those data. So you can think about it as an infinite sample of hypothesis. because every set theta in this space, or every value of the Rydberg constant in the continuous real number space, will give you a different hypothesis. Okay. So what are you trying to pick is that given this data, given this observed data, what is the most likely hypothesis? So remember, I have an infinite set of hypotheses because this R can have infinite value in the real number space. Okay. So what are you trying to do here? What is the value of R that is most compatible with this data? Okay. And then that is the kind of the best fit value of R, you call it. Okay. So basically, from a infinite pool of hypotheses, if your hypothesis depends on a parameter, okay, and if the parameter has a continuous range of values, sometimes the parameter can be discrete as well, but assuming that it has a infinite range of like infinite number of values, then you are basically trying to pick out from the information of data what is the most likely value of R, and you call it the best fit value of R. Of course, that
Category.
yes,
Hello.
yeah. Tell me.
So this category 3 and category 1 are similar, right? In category 1, we said that we have two hypotheses and we have to choose one over another. And in 3 is generalization of that.
You can visualize that like that, but here you have uh, infinite you have an infinite pool of that hypothesis. Okay. You are not so in the category 1 you have a finite sample space for hypothesis. In category 3 you have an infinite sample space of hypothesis. Okay. In category 1 there is no unknown parameter. Okay. Those are called simple hypotheses in a sense. In category 3 you have hypothesis that depends on a parameter, so they do not give you unique prediction. Okay. So they give you predictions that depends on certain parameters. Okay. I'm not sure if I made this clear enough, but wait till I get into the details of these things, and then perhaps things will be more clear. Okay.
Okay.
Uh, all right. So here, as far as the example I gave here is the atomic spectra where your Rydberg constant is an unknown parameter. Okay. You do not know that parameter. I am just trying to make it conform to the other two categories. I am basically trying to put in same type of language so that this can be described in the same way. Okay. All right. So this R usually could have infinite number of values, and our job would be to choose one value, and you call it the best fit value. And there would be an uncertainty around that best fit value. We need to also specify that. So R is so for example, what I want to do here. So suppose someone did this experiment once, and that person got the value x1, x2, and so on and so forth, and he quoted a best fit value here. Okay. Now another person will can repeat, because these experiments are repeatable at least in your mind infinite times. Okay. And that person got different values x1 prime, x2 prime, and so on, slightly different values. Okay. That person will get value another, let's say green R best fit. Okay. Then which one do I believe? Okay. If two independent groups does the same experiment to determine Rydberg constant and give me two different best fit values, I do not know which one to believe. Okay. So that's why it is always imperative that when you are quoting the best fit values, you also quote the uncertainty associated with the measurement. Okay. The uncertainties can have two sources. One is due to the finite nature of your measurement. You only have a finite amount of data. And also the second set of uncertainty, which is the most dominant, is the uncertainty associated with the measured quantities themselves. Okay, this x1, x2 are not uniquely determined, but they are measured with certain uncertainties. So it will translate uh, into an uncertainty of this r. So you will quote, let's say r equals 0.03 plus minus 0.0009. Okay. So what it means is that this r has a range. From this measurement, if you quote this value, that means from this experiment, uh, R is located around 0.03, but the experiment is so precise, this measurement tells you that if this is repeated theoretically infinite times, the best fit values in all those hypothetical measurements will turn out to be within this range. So 0.03 plus 0.009 to minus 0.009. So this best fit of an alternative measurement will fall into this range 68% of the times if it is repeated infinitely. Okay. And 95% of the times if I extend it to 2 sigma. So this is what it means. Okay. So this is your goal in the third category of examples. Okay. So this I will call it to be parameter estimations. Parameter estimation. Okay. So there are three types of statistical inferences or decision making scenarios that you will encounter. First is sampling of data. Second is hypothesis testing, okay, or goodness of fit test. And third is parameter estimation. Okay. Once we cover that, then we are almost done with this course. Okay. So this will be my next course, that we will do more of a practical statistics, and this will involve a lot of computational work. So I will need your help, of course, and you should do these examples religiously. You will be doing this, and every day one of you will be starting with your computer and doing the fitting, and how to do those fitting we will learn it. This is more practical. Okay. So with this, I will probably end here, and I will let you know when is the next class. Probably quite soon, maybe this week again. I will let you know in the Google Classroom page. So now I will briefly pause and see if there are questions. No questions? All right then. Okay, I then stop recording.